Here are two programs, both sort a list, both hand back the exact same answer. On a list of 1,000 things, you could never tell them apart. Now feed them a few million. One finishes before you blink, the other is still grinding when you go home for the night. Same output, same machine. The only thing that changed is how each one scales, and honestly that's the most important thing to understand about any code you write. It's called Big O notation. By the end, you look at a function and know whether it survives real data, where its memory goes, and when the math quietly lies to you. I'm at pattern repetition. Let's get into it. Start with the obvious objection: why not just run the code, time it, and be done? Because a stopwatch measures your machine, not your algorithm. 200 milliseconds on your laptop is a different number on a phone. Different again on a server or on a hot afternoon with the fans screaming. The code never changed. The hardware did. You need a measure that ignores all of that. That measure is Big O notation. Instead of counting seconds, you count operations and you ask one thing. As the input grows, how fast does the work grow with it? Double the data, and does the work stay flat, double, or explode? That's a property of the algorithm itself. It holds on any machine ever built. Big O has a real definition under the buzzword. Here's the whole thing in one line. Your running time, f of n, is Big O of g of n if past some starting point f never grows faster than g times a constant. Plain version, g is a ceiling. Your algorithm's cost stays under that shape forever once the input gets big enough. The whole game is picking the right g. So you analyze real code by counting the work line by line. A setup line is constant, one loop over the input is linear, a loop nested inside another loop runs n times n, so it's quadratic. Add it all up and you get n squared plus n plus a few constants. Then you throw almost all of it away. Drop the constant factors, drop the smaller terms, keep the one that grows fastest. This whole function is O of n squared, because once the input is large, that nested loop is the only part that still matters. One bit of vocabulary people always mix up. Big O is the upper bound. The worst case, the ceiling. Big omega is the lower bound. The best case, the floor. And big theta is when the floor and the ceiling are the same shape, pinning the growth exactly. In practice, engineers almost always quote Big O because the worst case is the one that pages you at 3 in the morning. Enough theory. Let's meet the handful of shapes you'll actually run into. Best to nightmare. Here's why this matters on one screen. Say your input is 1,000,000 items. A constant algorithm does 1 unit of work. A logarithmic one, about 20. A linear scan, 1,000,000. A good sort, 20 million. But a quadratic algorithm needs 1,000,000,000,000 operations for that same 1,000,000 items. An exponential doesn't even fit on this chart. We'll get to why. This is exponential growth on its own. Every time you add just 1 to the input, the work doubles. At n equals 10, 1,000 operations. At 20, 1,000,000. At 50, you pass the quadrillion. Add one more item and the whole thing doubles again. Exponential algorithms don't get slow gradually. They fall off a cliff. Now let's walk each shape with real code, fastest to slowest. This is the part worth memorizing. Start at the top, constant time, O of 1. Grabbing the 5th element of an array or reading a key out of a hash map. Same time whether the collection holds 10 items or 10 billion. The computer jumps straight to the address. No searching at all. This is as good as it gets. Next, logarithmic, O of log n. Binary search on a sorted list. Check the middle. Too high, throw away the top half. Too low, throw away the bottom. Every step deletes half of what's left. Halving is exactly what a logarithm counts, and it's absurdly powerful. How powerful? Take a sorted list of 1 billion items. A linear scan, one at a time, could take 1 billion comparisons. Binary search finds anything in that same list in at most 30. 1 billion versus 30. That's the whole difference between a straight line and a logarithm. Now it starts to hurt. Quadratic, O of n squared. A loop inside a loop, like bubble sort comparing every pair. 100 items is 10,000 steps. 10,000 items is 100 million. The work grows with the square of the input, so 10 times the data is 100 times the work. Nested loops are where naive code quietly dies. Which is why good sorts avoid nested loops. Merge sort and quicksort run in n log n, that sweet spot just above linear. Sorting the same 10,000 items, bubble sort does 100 million operations, merge sort does about 100,000. And n log n is provably the floor, no sort that works by comparing pairs can ever beat it. Then there's exponential, O of 2 to the n. Here's the classic trap, naive, recursive Fibonacci. To get fib of n, it computes fib of n minus 1 and fib of n minus 2. And each of those splits again and again. The same values get recomputed thousands of times. Fibonacci of 50 spawns roughly a quadrillion calls. This tiny innocent function will freeze your machine. And at the very bottom, factorial time, O of n factorial. That's trying every possible ordering, like brute forcing the traveling salesman by checking every route. 20 stops gives you 2.4 quintillion orderings. Add one stop and you multiply by 21. These algorithms work up to about 12 items and then never again. Time is only half the story. Every algorithm you just saw also has a memory cost, and that's the half people forget to check. Space complexity asks the same question about memory. The number that matters is auxiliary space, the extra memory you use beyond the input itself. Heap sort rearranges the original array and needs almost no extra room. We call that in place. Merge sort needs a whole second array to merge into, so it spends O of n extra memory. Same time, very different memory bill. And here's the sneaky one. Recursion isn't free. Every time a function calls itself, the computer saves a stack frame, and those frames pile up until the deepest call finally returns. A recursion that goes n levels deep quietly uses O of n memory on the call stack, even when the code looks like it allocates nothing. Go deep enough and you don't get a slow program, you get a stack overflow. So time and space are two separate budgets, and the most useful trick in this whole field is spending one of them to save the other. Go back to that exponential Fibonacci. It was slow because it solved the same subproblems over and over, so stop doing that. The first time you compute fib of a number, write the answer in a table, next time read it straight back. That one change is called memoization, and it drops the cost from 2 to the n down to n, exponential to linear. But look at the full ledger. Naive recursion, exponential time, and O of n stack space anyway. Memoized, linear time, but now you're holding O of n memory for the table. And if you only ever need the last two numbers, an iterative version is linear time and constant space. Best of both. You paid memory to buy speed. That's the time-space trade-off, and every cache and lookup table is the same bet. One more idea that trips people up than the honest fine print. What does an operation cost when it's usually cheap but occasionally brutal? Take a dynamic array, the list you append to every day. Usually a push just drops the value into an empty slot. Constant time. But when it fills up, it has to grab a bigger block of memory and copy every existing element across, and that copy is O of n. So, is push fast or is it slow? The honest answer is amortized. You double the capacity every time you grow, so the expensive copies get rarer and rarer as the array gets bigger. Add up all the copying across 1 million pushes and it totals less than 2 million operations. Spread out, every push averages constant time. We say push is O of 1 amortized. Rare pain, cheap on average. Big O is the most useful tool you've got. It's also a liar in 3 specific ways worth knowing. First, it hides the constants. Big O only cares about huge inputs, so for small ones, a worse class can win outright. Insertion sort is quadratic. And it still beats those fancy n log n sorts on tiny arrays because its constant is so small. This isn't a footnote. Python, Java, and Chrome all quietly switch to insertion sort for runs under about 64 elements. Second, worst case and average case are different animals. Quicksort is n log n on a normal day. Feed it a pathological input and it degrades to n squared. A hash lookup is constant on average, but if every key collides, it's linear. When somebody quotes a big O, always ask, is that the worst case or the typical one? And third, big O measures growth, not speed. It tells you how your code scales, never how many milliseconds it takes today. An O of n algorithm with a giant constant can lose to an O of n squared 1, right up until the input gets big. Big O tells you which one wins eventually. Only a benchmark tells you which one wins right now. Which is why the most famous line in all of programming is a warning about exactly this. Donald Knuth. Premature optimization is the root of all evil. He wasn't saying ignore performance, he was saying don't twist your code for speed you can't prove you need. Measure first, then optimize the 3% that actually matters. 5 things to take with you. Count operations, not milliseconds, because growth outlives your hardware. When you analyze code, keep only the dominant term. Nested loops and unguarded recursion are where quadratic and exponential costs love to hide. Spend memory to save time when the numbers justify it. And never optimize a thing before you've measured that it's actually slow. That's time and space complexity. 2 programs, the same answer, wildly different futures, and now you can see the difference before you ever hit run. Don't count the seconds, count how the work grows. I'm at pattern repetition. See you in the next one.